Plan of attack today is to kind of briefly introduce optimization. We're going to look at this problem, and then I'm just going to help do the codes with you. Okay, we'll probably make the function code first, and then make the main code. Okay, so basically, what we're going to do is we're going to do what they call a golden section search optimization problem. Okay. And I'm going to talk about what this golden search means, the process. But hopefully you look at this and you can kind of tell me what this is. Can you tell me what this is? Sure, it is. Perfect, right? They're forces. It's a differential equation. This right here is a drag force. Okay. This right here, I'll talk about here in a second. It's pretty much like a traction force, depending on the number of axles you have, which is little n, and the torque of the motor. Okay, good. And over here is this MA, right? And if you notice, this stuff, we spent half of the semester trying to solve, right? If I gave you all the values for this and said, try to solve for acceleration and velocity, you could do it. Okay. So there are times where, again, you have to kind of derive a differential equation from some of the forces and solve it. What we're going to do is we're going to take this differential equation and we're going to solve it, but we're going to change. Do I have it here? No. We're going to change the little n, which is the gearbox ratio or whatever. Okay, gear train. And what we want to do, and if I scroll to the next one here, I don't know how to flip it here. I flip this. I guess you could just turn your head. Basically, you have this train track or train system that is trying to go 400 feet. Okay. Depending on the gear ratio that you have, okay, you could get there quicker or you get there longer, right? Does that make sense? So if we change a gear ratio, it's going to cause the train to go slower or faster. So what we're trying to do, we're going to write a code that finds the minimum time depending on the gear ratio. Okay. So what we have is this train has got to accelerate, which is this differential equation, from 0 to some feet. And then it has to decelerate to slow down. So the deceleration equation is right here. It's constant, where Ca is the coefficient of adhesion between those, between the wheels and the train track or whatever. Okay. So we have this train that starts at 0 feet. It's got to go, I think, 4,000 to 4,000 feet. It needs to accelerate, decelerate. We're going to change the gear ratio, which is little n, the optimal gear ratio, little n, and we're going to try to figure out for that gear ratio the shortest time. Okay. So if we pick a gear ratio from 1 to 20, somewhere in there, it's going to be the shortest time. Okay. So if I go to this, let me move this up here. This plot right here, I did it. This is time versus gear ratio. Okay. So the way that I did this was I plugged a gear ratio from 0 to 4. Actually, I think I did like something 0.1 or something to 4. Okay. And for every gear ratio, I solved that differential equation. Both of those, acceleration and deceleration, and I got this line. Okay. If you notice, it goes down and then it hits a minimum right around 2.4. That's what the number we're going to get. Then it goes up slightly. It's hard to tell in here, so that's why I made this graph. Okay. And this PowerPoint and that PDF should be in Blackboard that you can grab. Okay. So this is a little bit zoomed in for time versus your gear ratio. Okay. So I could have just told you, make a matrix from 2 to 4, plot it, look for time and tell me the best gear ratio for the smallest time. What would you tell me? It was 2.4. Okay, that's one way of solving an optimization problem is you graph it and you point it out. Okay. What I'm going to show you is this golden search where we pick two n values to start out with. See this black star and the red star? These are two values that I can input into the code, and I'm going to say, okay, I'm going to start with these two values first. So I started with 3.25, 2.75. Okay. The way that this optimization problem works is it compares these two dots. If this dot is higher than this, which higher time, then what we're going to do is we're going to basically hide everything to the right, okay, because we know that that time value is higher. We don't have to worry about that. And we assign two new values. So if you look here, you see how I said, well, 3 is equal to 2. Okay, so we keep this, but then we move to the left and we make a new point to the left, and we call that point 4. Okay. Is 3 higher than 4? In this case, for time, it's slightly higher. Okay, so what we do is we then get rid of stuff to the right and we make a couple new points. Okay. I added this graph in here. These lines right here are actually points 1, 2, 3, and 4. But remember, 2 and 3 are the same, so technically there's 4 lines on here. These lines indicate each n value. Okay, so there's 4 different n values, 4 different points. This is velocity versus time. Okay, this curved part, acceleration, and then from here down is deceleration. Okay, and you're going to see at the end, I did a lot of n values of these. Okay, and it actually kind of converges to a section. And then what happens is I put this plot here. Here's our initial 1, 2, and then 3, 4. And then I pick new points, 5 and 6. Well, 6 now is higher. So then we go to the right. We define 7 and then we define 8. Okay. So this is an optimization. This is how we do it. We're going to write the code so it looks at each value and says, no, we have to define this. And then this last line is all the iterations that I did, velocity versus time. And you can kind of see it like converges almost to one line because that's what happens. Okay. All right. So we're going to do a new script and then make a new function script. And I'll put it over here. Oh, this is it. Yeah. We have optimized our homework assignments. Can I? Oh, perfect. Okay. All right. This is homework 12. Yep. Here's a function t. Let's call it homework 12 function. And we're just going to put n. WARNCAG What's that? Oh, it does. One kajak. Oh, I don't need to put that. I'm just going to do it. I'll write some stuff down. I didn't comment everything, so. File DT is less than equal to 4,000.
4,000, please, your time. Takes that long.
4,000 is the feet. The feet total, that's the total distance that we need to go. Yep. And this W of the motor is the angular velocity of the motor, okay? Depending on your gear ratio, N. All right, keep chugging, keep chugging. So the torque's going to change. So if W of the motor greater than or equal to 106, the torque of the motor is 29.9 times 10 to the 9th divided by W of the motor raised to 3.13.
MATLAB recognize E.
Yep. Yep, it does. Yep, you can do that. The drag force. 3 W divided by 2,000 plus 29 times normal force 0.03 times V of J. Oh. I have to make it a little bit bigger, I guess. 8 times. Yeah, times V. This is times 60, right about 88. So we're dividing the W by 2,000 because it was in tons. W has to be in tons, just to let you know. No, it was, I think it was in, yeah, it might have been. Yeah. 0.3, 29. And big N is the number of axles, which we'll define. We may, I'm not sure, I didn't notice this, but I'm not sure what the 60 divided by 88 is.
Must be a factor, like per unit difference. On what?
We'll keep going with it. We'll check it.
Maybe you can get them all.
No, I can't remember. That's one thing I missed. We'll get back to it. Okay. F, little f, which is really the acceleration. G divided by W times N times little n times T of the motor divided by R minus FD.
The velocity is miles per hour.
Oh, that could be, yes, I bet you it is. What,
It'd be 3,600.
so miles per hour to probably feet per second, I bet. Yep. I can check on my computer here. Or V is in feet per second. I don't know if I put the units right. The units might be, it might not be meters per second. So I hope so far it's kind of making sense, right? We're defining values. And then this line 20, I'm calculating the next velocity, which you've done before, by using the previous velocity. This F is really acceleration times the delta T, okay? Which gives us velocity. Now I'm going to go down here. Mathematic equations. D, J plus 1, D of J plus V of J times delta T plus F of J times dt squared over 2. Yep. So if you look, my line 23 uses the velocity on line 20 to find what the distance would be for the acceleration phase. Line 24 actually uses that velocity at that instant and says, what is the distance from that velocity to 4,000 feet, if you want to think about it, okay? And then I added those two together. Line 24, let me make sure I have this because you probably want to remember how to do this. Maybe where did it go here? Right here. So line 24, that distance from this point down to here, this linear line is found by using these two equations right here. Okay. This is your velocity equation when you have constant acceleration, because this is your deceleration phase. And this is the distance when you have a constant acceleration. What they did was they plugged in, they solved for this time, they plugged it in here, and they got this right here. They basically said that T2 minus T1 is V naught over CAG. They plugged it in this equation, and they ended up getting this for your distance equation, okay? So just two equations, two unknowns, only for a constant acceleration, okay? So just be aware, if you're watching this back or you download this in a few years and you're like, how, where did that come from? That's where line 24 came from, okay? Then I added those two together, okay? Now, we can figure out the time. Take our increment, and then we have to increment our J value. Okay, no one here? On this, you see line 32, I have V of J minus 1. Remember why we should put that? Why isn't it just J? J while loops. Exactly, yes. So when you do a while loop, you always have to remember it'll go one number above the number you assign, so it could be 4,001. So the correct value would be the value, subtract one, okay? So that's why I have J minus 1 here, and same thing for the time, okay? The time is actually also, because it's over 1, okay? Then, same thing with DOT, and then I said, well, T, if you go all the way to the top, that's our output. That's the total time that we're looking at. Okay. Yes, I think I was just looking at what that value was later. I think if I took the semicolon off here to see what that value was. Yep. I didn't assign it to anything. Yep. Yep. I probably could have taken it out, but that's fine. Okay, let's keep going here. I'm creating basically time matrix and a velocity matrix for the deceleration phase. And you'll see once we get it. Let's plot it. Would you say the velocity was probably feet per second? Yep. Yeah, so my time is wrong on the graph, but that's fine. If you haven't saved it, and make sure it's called homework 12 function. Whew. So what this function code is going to do is we're going to input an n value, gear ratio. It's going to run through this while loop. And it's going to calculate velocity only for the acceleration phase. Okay. And the time. It only calculates velocity and time for the acceleration phase. But then it uses that velocity to calculate what the distance would be at that time to start decelerating to 4,000 feet. Okay. So it's finding the velocity and time for the acceleration, but then also the total distance that it would go. After the loop, we basically are looking at trying to find the total time by calculating the time it would take to go, that deceleration time, okay? Creating a matrix for it and then plotting. So we'll plot the acceleration and the deceleration phase, okay? So save it. And let's create a new script now, which I think I already have one open right here. And I'm going to put this to the right. PLC, clear all, close all. And then global, WARNCAGDT. And let's define our givens. View 35 times 2000. A 100. R 15. N is 4. CA 0.15. G 32.174. GT 0.001. And gamma 1 plus SQRT 5. It's actually, you'll see, pretty short. We're going to enter NS, this guess or this start value. NF start. So line 20 is slightly different than what we're normally. I just wanted to show you that we can call functions this way too. Okay. So I'm going to write a few more lines and then we're going to run it to make sure it works. Once you get to that point, run the code, make sure it works. You should get a graph. Actually, you probably should get 2 lines maybe. Actually, let me run it, make sure. Put 0 and 4. Index exceeds array bounds.
Something.
Did I miss something? Is this supposed to be? Oh, I know why. Right here, line 25. Do +1. Yep, it's because it wasn't creating the next value. So fix that on line 25, do +1 for DOT. And now I'll go back and run your code. Should get 2 lines. Now, you notice here too, that I'm not actually starting with 2 and 4 as my guesses for N. I'm subtracting and adding this ratio here. This is the golden ratio, if you want to call it. That's why it's called the golden search. It actually is a optimal, like this number here, this ratio, and when you take your difference and you divide by this ratio, that's called the golden search. That's the optimal distances or whatever you want to subtract between your points. Okay, so don't get too involved. That's just a number that we use. Okay. All right, so I think everyone got to this, right? If you run it again, I'll do 2 and 4. I think that's where we left off because I wanted to make sure everyone was right there. Okay, so again, this is the acceleration phase, and these are the deceleration phase. And I don't know which one is first. Maybe is the blue one first, or is the orange one first? 2.4. I think 2.4 was. I don't know. But each one of these lines represent a different gear ratio. Okay. Okay. So let's keep coding. I could do like a pause, like I could do pause and run it again. So the blue one is 2. Yep. Okay. Yep. Cool. All right. Take that pause out. All right. So let's write the code now. So count equals 0, while delta is greater than 10 e to the minus 7. 1 is greater than T2. 1 is greater than T2. Oh, I have a parenthesis there. Oh, we can put this, sorry, we can put case A, T1 greater than T2. I thought I put that in there, but I must not have. And 2 is NS plus delta divided by gamma. T2 is T of N2. Count equals count plus 1. So in this part, if I go back to the graph on the PowerPoint, it's basically, it's saying that like this point 6 is greater than 7. Okay. So what's going to happen is we're going to define this as N1, 7, and then we're going to make a new point called N8. Okay. Or if you want to call it, we call it, I think we called it N2. Okay. That's if you go to this, we define the information on the right, and then we use those values to figure out, we add some, so we move to the right, okay? So that's what this is. And then if it's the other way, this would be case B. T2 greater than T1 and F 2 is greater than T1. And F equals N2 equals N1. 2 equals T1 delta NF minus NS. N1 is NF minus delta over gamma. And final N1 equals count. So this is now saying that the second point on the right is higher. So we're going to get rid of everything to the right, define the new point on the right, and then subtract to find the new point. And then that's it. Then we can write stuff to the command window. Put your name here. Oh, yep. Thank you. And then go ahead and run it, see if it works. This is where I use the NS start and NF start there, Michael. I kind of defined it, but I'd have it later. I guess I probably could have deleted NS1 and NF1. I probably didn't even need those. Yeah, I don't think I ever used NS1 or NF1, so we could probably really take those out. You got two though? Or was it two? Let me check. If I do 0 and 10. Well, 0 and 10 didn't work, did it? Okay. Let's try 2 and 8. True. Okay.
Display NF.
Did I put the wrong one in? No, 2. I don't know. Maybe it is 2. Wait, no, the answer on the graph was what? 2.4? Yeah, it's still right here. Go ahead and finish it and we'll look at it. Oh. Got the crucial thing in here. What did I forget to do? Line 52, got to add it. In the else, we never put the new value that we established, this N1, back into the code to figure out the time. Now try it.
And then 2.4.
2.4, there we go. Okay. That's one way, or you can make this smaller. Okay, but I don't know how long it's going to take me, so I'm going to do 2 to 3. It may take a while on my code. So you can change the delta. Yeah, it's now processing a lot of information. It'll be fast on these computers. Yeah, but look, so look at my command window. It's jumping back and forth, right? It's on the right side of the bell, then it's on the left side of the bell, and then it's the right, left, right. You know what I mean? There we go. Worked. 2.4. That's exactly right. You know what I mean? Like 2.4 is enough. Like even if I bet you went to the 2, it'd be probably close enough. It's still going to take a long time to process this, but the number of iterations should be smaller. See that? That's pretty cool, huh? She just did optimization problem. This. So just to recap again. So if we have a train, and I don't know if it's on tracks, is it? It doesn't really matter, okay? Basically, you have this train, you have a traction force, you have 4 of them, because there's 4 axles, okay? These traction forces are really, you convert it into a gear ratio and a torque, okay? So you got 4 of those. So up here, if I go back, turn this 3 times, Here, this free body diagram, this shows the traction force. This is the number of axles, the gear ratio, the torque, motor torque, and the radius. Okay, so that's the traction force developed. Okay, I think it even says it here somewhere, I thought. Nope. Traction force. Here's the drag force on that train, and here's your MA term. Okay, just this free body diagram converted into a differential equation. What we're trying to do is if we change this gear ratio right here, it will actually develop different times it takes to go 4,000 feet. Okay, you have a gear ratio of 2, it's probably going to be maybe 5 seconds. A gear ratio of 7 might be maybe longer. Okay. So what we're trying to do is write a code that will optimize it to figure out the shortest distance. Okay. And just to show you what it looks like, I went and created my own graph. I wrote my own code and just looped through different n values. And this is the graph that you get. Okay. So it goes down and then actually slightly curves up. And the peak is right here around 2.4. Okay. Now, we go to the function code, which is right here. This code solves that differential equation, which we've done a couple times numerically, sort of. Okay. So initial velocity, initial distances. We're now saying we're doing a while loop. While this total distance is less than 4,000 feet, because that's how far we're going, we calculate the radians per second of the motor, which is in terms related to the gear ratio. All right. And the torque of the motor depends on this radians per second. We figure out the drag based on the number of axles, the weight, and the velocity. Okay, so as the velocity changes, your drag force is going to change. Line 19, that's your acceleration. Okay, I probably could call this A. I just called it F. I don't know why, but I could have called it A. Okay. Line 20 is basically saying if we multiply the acceleration, which is meters per second squared, times a second, which is delta t, this gives us meters per second. This is the, if you want to think about it, what that velocity is increasing at that delta t. And we add it to the previous velocity. So previous velocity plus this change in velocity gives us the new velocity. Okay. Then with the velocity that we found, okay, we can figure out the total distance that it went by using kinematic equations. Okay. This is the distance for the acceleration phase. Okay. Now, at that velocity, say we're going, I don't know, 10 meters per second. Okay. And we knew how far that went. And we looked at that velocity at that part. Okay. We can use that velocity to figure out what the distance would be to stop that train to go to basically 0 or the rest of the 4,000 feet. That's what this distance is right here. Okay. So this is the distance deceleration. This is the acceleration. And we just add those two up. Okay. Then this time right here is only the time for the acceleration. Okay. And then we loop it. Down here is we grab the correct velocity for the acceleration at the end, which we have to subtract 1 because it's a while loop. Okay. We calculate the time it takes with that velocity to stop. This then would be the total time. This would be T1, which is this, plus the time for acceleration. The total distance, again, we subtract 1 because that's a while loop. And then we just assign the total time to T. Okay. And then down here is just we create a matrix for the deceleration phase for time and velocity, and then we plot both. Okay, so that's what this code is doing. All right, and to be honest, there's probably another way you could do this. You could probably just look at acceleration and then have another for loop for distance for deceleration phase. I kind of combined them. Then if we look at the code, this is the main code. This is where we define our givens. We ask the user to input some values, and we pretty much kind of run those initial values to our function code, which is here. Okay. So line 20 and line 28 and 29 kind of go together. We're inputting a gear ratio, actually two of them, and looking at the total time. And if you go back to this graph, if we use 2 and 4, well, sort of like this is 2.75 and this is 3.25. These are kind of our initial points that we put in, and we compare these two. If this point right here is higher, then what we do is we get rid of that. We define 0.3 as 0.2, and then we subtract a distance, okay? And if you look, when T2, when the second distance is greater, okay, that's what we do. We subtract, we create a new point to the left. However, down here, if this point over here is higher than this, okay, then we need to add a point and we go to 0.8, okay?